Okay, good morning, everyone. So we've been talking about the shell model for atoms with many electrons. And when we do that, we're interested in the following facts about atoms. We're interested in the orbital occupation numbers, sometimes known as the electron configuration. And we're also interested in the angular momentum information, which is usually given in terms of the LS or Russell-Saunders spectroscopic terms. Okay, and that notation is we put a pre-superscript, which is twice the spin, the total spin plus 1, and then L with a letter code, and then J. And both of these things are approximations because they're approximations in which you're doing the central field method and you're treating the individual spin orbit couplings as a perturbation. So last time we did a couple of examples. I think we did helium, which we already knew the answer to, and we did boron. And so today we're going to do a bunch more examples, starting with an easy one, which is the noble or inert gases. Okay, and these consist of all atoms in which there is a full p orbital. Remember, p means angular momentum 1. And all other lower orbitals filled when you look at the orbital filling order. So, and all other orbitals filled. Okay, and so if we make a list of those, there's helium. Helium doesn't actually have any p orbitals filled at all. So that's 1s squared. And then neon is what you get when you take the helium configuration. So we often put that in square brackets to indicate that all of those are filled, plus a 2s squared, and then a 2p. Remember, each p orbital can have 6 slots to put electrons in. And so if it's totally filled, that's 2p6. And then argon is what you get when you take everything that's in a neon and you add 3s squared and 3p6. And krypton is what you get when you have everything in an argon plus 4s squared. Okay, but then the 3d orbital is next in the filling order, it turns out. So you have 3d10 and then 4p6. Okay, and that's just because the 3 is telling you that you're going to fill up the what we would have otherwise skipped in the filling order because it's a lower n, even though it has higher angular momentum. Okay, and then xenon is what you get when you fill up everything that would be filled in krypton, and then 5s squared, 4d10, 5p6. And so radon, the next one, is going to have 6p6, but you have to fill up everything that comes before the 6p orbital. So that's everything in xenon, plus 6s squared, 4f14, 5d10, and then finally you get to the 6p, and then you fill them all up and you have a noble gas. Okay, so that's the electron configuration for noble gases. And if you're interested in the, as we are, if you're interested in what's the spectroscopic term notation, since all of these have only filled orbital shells, they all have total spin 0. That should be just because every electron with, say, spin measured up is going to have another electron partner with the spin measured down. And actually the same for the orbital angular momentum. Okay, and then the only thing you can get when you add S equals 0 and L equals 0 is J equals 0. And so all of these spectroscopic terms for noble gases are 1s0. Okay, and so we talked last time about Hund's rules, but here Hund's rules are not necessary because there's only one choice for the ground state. Okay, now for anything that's not a noble gas, if you have the same shells filled for two different elements, filled, in excess of some noble gas configuration, then you're going to have similar chemical properties because those outer electrons are the ones that can combine with other atoms, similar electronic chemical properties. And so those correspond to things that are in columns of the periodic table. And so, for example, there are alkali metals. Alkali metals are what you get when you take a noble gas configuration and add one more electron to it. So for example, there's the first one is lithium, which is what you get when you take helium configuration, and the next electron shell that you can put it in is the 2s. And so we put one electron in the 2s, and then the next one is sodium. We just take the next noble gas, which is neon, and we add the next available shell, or the next available orbital, which is a 3s. And so the pattern continues. For potassium, you take argon and you add a single 4s electron. For rubidium, that's krypton configuration plus a 5s. For cesium, it's the xenon configuration, and then you add a 6s. And francium is radon plus a 7s. So those are the electron configurations. We don't have to write all of the shells out. We just write the noble gas plus the next one. And in all cases, since we're interested in the Russell-Saunders term, the only thing that matters is the one electron in the s shell in each case. And so this is going to be another easy example of Russell-Saunders coupling. If you only have one electron, then the total spin has to be 1/2. And notice we're always adding something in an S shell because an S shell is always what comes in the filling order after a P shell. So they all have orbital angular momentum 0 because it's an S. And the only thing you can get when you add spin 1/2 and orbital 0 is J equals 1/2. So again, there's only one possibility, and that's a 2 for spin, S for orbital, and 1/2 for the J. So again, we don't need Hund's rules for these examples. Okay, and then another thing you can do is halogens. So let me put it next to the alkali metal. Halogens are sort of the opposite. It's what you get when you have one electron less than a noble gas. So the first one would be fluorine. So you take helium, and then you add everything you can add until you get to a one before a noble gas, which is a 2s with 2, and then a 2p with only 5. So for all the halogens, we're going to have NP, and with 5 electrons in it. So chlorine is going to be neon, 3s, 3p, 5, and bromine is argon plus 3d10, 4s2, and 4p5. We can't forget, though, to put in the D shells in there. Iodine is krypton plus 4d10 and 5s squared and 5p with 5 electrons. And astatine is xenon. We just fill in everything until we get to a 6p5, which looks like this. 5d10, 6s squared, and then finally the 6p5. So just like for the alkali metals, if we look at this spectroscopic term notation, the only thing that's going to matter is the p5, the 5p electrons in each case. All the rest of this stuff doesn't matter when you're trying to figure out what the angular momentum is. So we just ignore all those things. And so these all have the same spectroscopic term notation again, which is all have 2p 3/2. Okay, and we will understand that a little bit more easily when we do some easier examples first. And so we'll come back to the halogens in a little while. Okay, so now we did boron last time. Let's do some more difficult cases. And so let's start with carbon. For homework, you're going to get to do some more cases that are somewhat similar to these, some of them more similar than others. So carbon has 6 electrons when it's neutral. And so if we just fill in these shells to figure out what the electron configuration is, first we fill in the 1s, then we do the 2s, and the next is the 2p. And once we put 2 of them in the 2p, then we're done, because 2 plus 2 plus 2 makes 6. And so now we'd like to figure out what the angular momentum configuration for this atom is in the ground state. So a good thing to do whenever things are a little bit complicated, a good thing to do is to first figure out what is the total number of electronic states associated with the unfilled shells. So first, we're just going to do counting. Count electronic states associated with the unfilled shells. So really, this should be the first step in any analysis of an atomic element. So in this case, what's the unfilled? The unfilled is the 2p, because 2p can fit up to 6, and there's only 2 of them. So that's the unfilled. And so we say the incomplete 2p shell has 2 electrons. And there are 6 slots that you can put them in. Because there are 6 p orbital states. And so the number of states that you can have is going to be the ways you can combine them antisymmetrically. And the way to choose 2 objects out of 6 is 6 times 5 divided by 2 times 1. Okay, and the 2 times 1 in the denominator is because we have to combine them antisymmetrically. And so that makes 15 states. So there are 15 states available, and we want to figure out what they are. And when we're done, we're going to check it by making sure that they really do add up to 15. Okay, so 2 electrons is a nice case. It's particularly easy compared to some other cases we're about to do. And it's easy because we can use what we already know about addition of angular momenta, and in particular, the symmetry and anti-symmetry properties of combining angular momenta. So this is because the anti-symmetry that we need is relatively easy to enforce. So let's do that by first, we're in the LS coupling scheme, first we add up all the spins as addition of angular momentum, then we add up all the orbital, and then we add those 2 together to get the total. So first let's do the spins. Combining 2 spins, when we do addition of angular momentum, we have a 1/2 tensor product 1/2, and we know that that can be either a angular momentum 1 in a symmetric combination or a angular momentum 0 in an antisymmetric combination. All right, and now let's combine the orbital angular momentum. These are our p states, and so this is a 1 cross 1. The 1 is because they're both p states. Okay, and if we remember what we learned about combining angular momentum 1 with another angular momentum 1, that's a 2 symmetric, a 1 antisymmetric, and then an angular momentum 0 in a symmetric combination. And so now if we want the full state to be antisymmetric, we just have to choose 1 from the first row and 1 from the second row in such a way that the the total is antisymmetric. So before doing that, let's make a little note here about more generally what we would do. Because who knows, for homework, you might encounter not some p wave electrons, but some d wave electrons, where instead of 1 cross 1 here, you might have 2 cross 2. Okay, and so more generally, if you have an angular momentum j combined with another angular momentum of the same type, then you can divide it into symmetric and antisymmetric combinations. So first of all, when you combine j with j, the maximum you can get is 2j. Here, j can be either the spin or the orbital. And if you combine j with j and you get 2j, that combination is always symmetric. The next thing you can get is you can get 2j minus 1, and that combination is always antisymmetric, and then they alternate. Okay, and in the end, the last one is always a spin 0 because you can combine 2 j's that are the same to get spin 0, and it will be either symmetric or antisymmetric depending on what you get when you do this in an alternating fashion. So when I put the ... here, it's understood that we alternate always between spin and antisymmetric and antisymmetric. Now that's what happens when you combine 2 like angular momenta. If you combine 2 unlike angular momenta, like you're combining a spin 1/2 and orbital 1, then it doesn't have any particular symmetric or anti-symmetric properties, and we'll have to worry about that in other examples where things will be more complicated. Okay, but this was a parenthetical aside. Okay, but these two things right here fit the pattern that we've just done. Okay, and so now we can look at, in this example, what combinations can we have that are totally anti-symmetric? So the totally anti-symmetric states are, okay, so one thing we can do is we can take an L equals 2 from here and a spin equals 0 from here. And then that symmetric and anti-symmetric makes a total of a symmetric anti-symmetric combination. Okay, so we can have L equals 2 and S equals 0. Okay, so let's write that in spectroscopic term notation. If S equals 0, that means the pre-superscript is 1. L equals 2 means it's a D state. Okay, and the only thing we can get for J when we combine 2 with 0 is 2 again. Okay, so that's the spectroscopic term notation for that state, except there are 5 of them because the degeneracy is 2J plus 1. So this is equal to 5 states for the purposes of our counting, because up here we said there were going to be 15 states total. So we found 5 out of 15. Okay, the next thing we can do is we can, instead of choosing L equals 2, we could choose L equals 1. That's this combination, which is anti-symmetric. And so if we want the whole thing to be anti-symmetric, then we better choose this one to be symmetric. Okay, so that combination is L equals 1. That forces the spin to be 1. And so the spectroscopic term notation, 2s plus 1 is 3. The L is the orbital, that's a p. But now when we add L equals 1 and S equals 1 to get J, J can be 0, 1, or 2. So this can be 3p0, it can be 3p1, and it can be 3p2. And so if we do the counting, for J equals 1, that there's 1 of those states. For J equals 1, there's 3 of those. And for J equals 2, there's 5 of those. So that makes 9 states from there. So now we found 5 plus 9 is 14. We found 14 out of the 15 states. There's only 1 remaining. And that 1 remaining is what happens when you choose L to be 0. That's symmetric, so the only thing you can choose is the spin, the total spin, to also be 0 to make it anti-symmetric. Okay, and so the last remaining state is L equals 0, S equals 0, which means it's 2s plus 1 is 1. L equals 0 means this is a S wave. And then the only thing you can get for J is 0. Okay, and the 1s0 is always just one state. Okay, and now if we add them all up, we indeed get 15. That's a good check that we have indeed found all the states. And now having found all the states, we can go ahead to decide which one's the ground state. That's what Hund's rule tells us. So for the ground state, we apply Hund's rules. Okay, and so let's remember what Hund's rules say. First of all, there was Hund's rule number 1. Hund's rule number 1 says that the one with the largest S wins. By wins, I mean it's the lower energy. So we want the sorry, largest, not lowest, largest, S. And the S is given by the pre-script, the pre-superscript. And so we see that that's going to be the 3 here. It's going to be one of those, or alternatively, we just look at the S, we notice that S equals 1 is the largest we can have. So that says the winner is going to be a 3pj state. Okay, now we apply Hund's rules number 2. Okay, and the Hund's rule number 2 is telling us that the state with the largest L wins, but these all have the same, the 3pj's all have the same L because they're all p states. And so that tells us nothing. It's not helpful. And that's because all remaining competitors have L equals 1. As indicated by the P, the capital P. So then we go to Hund's rule number 3. Okay, and Hund's rule number 3 is this test where you say, okay, first of all, is the last shell more or less than half filled? And the answer in this example is less, because we have 2 p shells, 2 p orbitals, I guess I should say. 2 p orbitals filled out of a possible 6. So it's less than half filled. And so that means that the J is going to be the smallest thing it can be, namely L minus S in absolute value, which in this case is 0. Okay, and so that selects that the ground state is actually this 3p0. And so we can conclude that for carbon, the electron configuration is 1s squared, 2s squared, 2p squared. And the Russell-Saunders or LS coupling term notation is 3p0. Oops, not 3p3. Okay. And so if you find a really fancy periodic table of the elements, it will give both of those pieces of information for carbon that we've just worked out. Any questions on this so far? Okay, so let's do a harder example, and this one's going to be nitrogen. Nitrogen has Z equals 7. So the first thing we're going to do is figure out the electron configuration. That's usually the easy part. We just start writing down the shells and filling them up until we get to 7. And so that's 3 2p electrons. And our next step is to count states. Again, when we count states, we just ignore the filled shells and only talk about the unfilled shells. They're the only ones that give that count when we're counting states. And so we have 3 2p electrons. And number of antisymmetric combinations is always then, it's going to be 6 times 5 times 4 over 3 times 2 times 1. And if we multiply that out, that's 20. So there are going to be 20 states. So that's going to be very useful because this one's a little bit more confusing. And when we get to the end, we want to make sure, if we think we've got all the states identified, we want to make sure they add up to 20. Okay, so that's the next question is, how do they divide into 2s plus 1 Lj Russell-Saunders multiplets, or terms? Okay, and so to do that, we'll just naively start constructing the addition of orbital and spin angular momenta. And I'm going to write naively here. It's naive because we know that in the end, what we have to do is apply total antisymmetry to the states that we find. Okay, so for L, what we're doing is we're combining one, because these are P states, one tensor product one. And we do that in pairs. So for the first one tensor product one, that gives 0 or 1 or 2. We write like that. And then we're tensor producting that with 1. And the thing we're going to get out is 0 tensor product 1 is 0 plus 1. And then we do the 1 tensor product the 1, and we get 0 plus 1, oops, plus 2. And then when we do 2 tensor product 1, we get 1 plus, I'm doing a bad job writing this. Sorry, we get 1 plus 2 plus 3. And now the problem is, if you look at these from a point of view of symmetry or anti-symmetry, some of these are just mixed, and you can't assign them any particular symmetry properties. One that you can is the angular momentum 3 state, which is going to be a symmetric one. So I'm going to put a little s for symmetric. And the other thing you can do is you can have an anti-symmetric combination, which is what you get when you do when you have one of these zeros. So this one's going to be anti-symmetric. Doesn't actually matter, except that I put one too many zeros, because here when I did 0 tensor product 1, that should have just been 1. That's the only thing you can get. And so this one should not have been here. Okay. So let's make sure that we have added these all up correctly. So the check just for the L states is when I have, let me write down the degeneracy of each one of these. So for L equals 1, that's 3. This is 1 state. This is 3. This is 5, 3, 5, and 7. So let's see, when I add that up, I get 3 plus 1 is 4, 4 plus 3 is 7, plus 5 makes 12, 12 plus 3 is 15, 20, 27. Okay, and each spin 1 has 3 states, so it's 3 times 3 times 3, so that's indeed 27. So this was just a check, not counting the electron states. This is just counting the naive angular momentum states when I combine 3 orbital angular momentum 1s. So the reason this 27 is bigger than the 20 is because we need to apply total antisymmetry of the state, and so most of these will not be actually physical. Okay, so that was the check for L, for combining the L's. And now for the spins, we have 1/2 tensor product 1/2 tensor product 1/2. Okay, and so if I combine the first two, there's a 0 antisymmetric plus a 1 symmetric, which I'm then combining with another spin 1/2. So that's going to give 1/2 plus 1/2 plus 3/2. And the 3/2 is the symmetric combination, but the two 1/2 don't have any particular symmetry property. In fact, they're not anti-symmetric. They're not totally anti-symmetric because if I have 3 spin 1/2, there's no way to form an anti-symmetric combination. One way of thinking about that is each spin is either up or down. And so if I'm trying to do it anti-symmetrically and I have 3 spins, then one of them has to be the same as one of the others. And so there's no way to make an anti-symmetric combination. So unfortunately, in this example, we only have symmetry information about some of the angular momentum states, namely this one and that one, and some of the spin states, and not about the others. So we have to do a little bit of logic here to figure out how to combine these things into anti-symmetric combinations. Okay, so to do that logic, so I should say here, these are mixed symmetries. And most of these are also mixed up here. So all of those are mixed symmetries. All right, so let's say we're going to form something out of the L equals 3 combination. So let's say L equals 3. That means the spatial wave function associated with the orbital angular momentum. There, in that case at least, we know that it's totally symmetric. And so if that's going to be part of our state, then we need the spin to be totally anti-symmetric. But there is no totally anti-symmetric spin state that you can make out of 3 spins, as we said. So, but there is no totally anti-symmetric spin state for actually anything more than 2 electrons. So for greater than or equal to 3 electrons. So we conclude from that that actually L cannot be 3. Even though it's in the list here of the allowed things, when we actually try to make an anti-symmetric state out of it, we can't. So that one we can just cross off. Okay, so we conclude L cannot be 3. Okay, let's look at what happens if L equals 0. L equals 0 is that one, which is anti-symmetric. So if L equals 0, then the spatial part of the wave function is totally anti-symmetric, which means the spin part better be totally symmetric. So spins symmetric. And so that means that S has to be 3/2. So one way of thinking about that is one of the members of that anti-symmetric multiplet, or that totally spin symmetric multiplet, is when all spins are up, for example. Okay, and so that's an allowed combination. Conversely, okay, if the spin is 3/2, then it's totally symmetric. And so then the orbital would have to be totally anti-symmetric. And the only one there is L equals 0 again. So that's the only allowed one. Okay, so let's make a table of the things that are possibly allowed. One is L equals 0, S equals 3/2. Okay, and the number of states there is 1 for the L times 4 for spin 3/2, because it's 2 times 3/2 plus 1. So there are 4 states. Remember, we're trying to add up to 20. Another thing we can have is L equals 1, but then S can't be 3/2, so it would have to be 1/2. the number of states there is 3 for L and 2 for the total spin, so that's 6 states. And then another thing we could have possibly is L equals 2 and S equals 1/2. And there the number of states is 5 for L because it's 2 times 2 plus 1 times 2 for spin. So that's 10 states. So now if we stare at that, we realize that, aha, if we just add those up, we've got 20. And 20 is what we know we're supposed to end up with. So that must be, in fact, all of the possibilities. So you might think, well, maybe I could have 2 copies of this, but then I would have for sure the 4 plus 12, and then there's no other multiplets that I can write down that would fill out to 20. And if I had 2 of these, that would already be 20, so I can't have that. And so this is really the only set of possibilities. Okay, so those are the L's and S's we can have. And now we just add them together to find the J's. So here, J could be 3/2. If we add 1 and 1/2, that can be 1/2 or 3/2. And if we add 2 and 1/2, then J can be 3/2 or 5/2. All right, so now we've worked out what all the Russell-Saunders multiplets are. Namely, I'm just going to write them all down: 4s 3/2, 2p 1/2, 2p 3/2, 2d 3/2. I'm just translating the information above into the code. Okay, and now we apply Hund's rules. Hund's rule number 1 says the first thing we should do is maximize S to find the ground state. Okay, and the biggest S is 3/2. That's this one, otherwise known as the 4s 3/2. And once we do that, there's only one multiplet there. So we're done. So 4s 3/2 is the ground state. Okay, so that was a fairly hard example to get right. Let's go on to the next one, which is oxygen, which at first sight is going to look even harder, but there's a trick to it that makes it easier. So oxygen has Z equals 8. And so the electron configuration, we fill out orbitals until we get to 8, which is 2p to the 4th in the last one. The next question we ask ourselves is, how many states are there? And so we need to take our 6 slots for the p orbital and ask how many ways can we choose 4 things out of them. And that's 6 times 5 times 4 times 3 over 4 times 3 times 2 times 1 makes 15 again. And now we would have to perhaps worry about all the different possible ways to combine angular momenta to get 15, but it turns out a better way to think of it is to consider the absence of an electron as what we're counting. So better is to consider the 2 holes, which are electrons that aren't there. So electrons omitted from the complete 2p shell. So the reason we can think of it that way is we know if we did have a complete 2p shell, then all the electron angular momenta would pair up and be opposite, and there would be no angular momentum at all. So there the counting is, now we're taking 6 hole slots, and we're choosing 2 of them. So the combinatoric says it's 6 times 5 over 2 plus 1, which is 15, which notice is the same answer that we got here. So that's good. And so our logic is the complete 2p shell has, we know, S equals L equals 0. And so we treat the holes, or the absence of electrons, as carrying the angular momentum. Okay, this is a lot easier than combining. We would otherwise have to combine 4 different angular momenta for spin, 4 different angular momenta for orbital, then figure out which combinations of them make antisymmetric combinations. But here, if we have only 2p holes rather than 2p electrons, then it's the same as what we already did for carbon. Okay, so the allowed Russell-Saunders multiplets are same as if it was 2p2, which is what we had for carbon, which we already did. And so we can just steal the result we got there for the possible multiplets. There's 1d2, 3p0, 3p1, 3p2, 1s0. And now we need to apply Hund's rules. And naively, you might think the Hund's rules are going to give the same answer as they gave for carbon, but there's one slight difference. Okay, so the first Hund's rule tells us it's going to be one of these because they have the largest total spin. So Hund number 1 says the ground state has S equals total spin 3. Just like for carbon, Hund's rule number 2 is no help because they all have the same orbital angular momentum. And now for Hund's rule number 3, that's where we have to be careful because Hund's rule number 3 always applies to the electrons. It doesn't matter whether you are using this trick about talking about holes rather than electrons. So the 2p shell is still, is greater than or equal to half filled, even though we've been talking about the holes, which are less than half filled. It's always the electrons that count. It's greater than or equal to half filled because it's 4 out of 6. Okay, and so the J that wins is the largest one, not the smallest one. And the J that wins is going to be 2. Okay, so that means that of these, the winner is going to be this one, the one with J equals 2. And so 3p2 is the ground state. Okay, let's quickly do one more example, and that's going to be fluorine. With our new trick about holes, that's going to be pretty easy. That has Z equals 9. The electron configuration, we just write things down until we get to 9, which is 2p5. Okay, and so we're going to treat this as one missing electron, or one hole. There's one missing electron in the 2p orbital. Okay, so one missing electron, or one 2p hole. Okay, and so the Russell-Saunders multiplet is
I'm sorry, Professor, is that a 5 or a 3? A 2p?
That's a 2p5. Sorry, let me rewrite it. Okay, so the Russell-Saunders multiplet has L equals 1, S equals 1/2. There's only one hole, but we can combine that into two different J's, 2p1/2 or 2p3/2, because those are the possible J's. Okay, so this is just like what we did for boron, but with electrons replaced by holes. Okay, and now we apply Hund's rules just like we did before. Hund's rules number 1 gives us no information because they all have the same S. Hund's rule number 2 also gives us no information because they all have the same L, namely L equals 1. And Hund's rule number 3 says, aha, the shell is more than half filled. Namely, there are 5 out of 6 in the P shell. And so we should choose the J that's the largest, which is 3/2. Okay, and so the ground state is the 2p3/2. Okay, and again, the way that these things are checked is you look at transitions between different states. You can tell which one's the ground state because it's the one where you end up with when you have different atomic states decaying into other atomic states. And so by selection rules and other information, the strength of the spectral lines and things like that, you can infer what the angular momenta are and check that these things are in fact correct. Okay, so next time we will talk about a defense of Hund's rules, sort of a qualitative discussion, a little bit more of why Hund's rules work. And then we'll talk about the limitation of Hund's rules because Hund's rules start to fail for larger atoms. And we'll talk about the classic example of lead, where instead of using LS coupling, you use something called JJ coupling. All right, so we will do that next time. And then also next time, we will start working on a totally new topic, which is going to be time-dependent perturbation theory. All right, any questions on today's lecture?
So I just wanted a quick reminder for myself. In these, I was reviewing this. I was trying to review it this morning too. That in that tensor product, when you turn the tensor product to a, what do you call it, the sum?
Yes.
So is it just like you start with 2j and then you go 2j minus 1 until you get to 0? Is it like you start with the sum of the two and then until you get to 0? Is that how it works?
You're talking about here, right?
Yes.
Yeah, so you start with the sum of the two, but you don't necessarily go to 0. You go to the absolute value of the difference of the two. Now, in this case, they happen to be the same. So when you take the difference, you get 0. And so in this case, that's why you end up with 0 when they're the same. But if they were not the same, let me write it here. Okay, if you were doing J1 tensor product J2, okay, the one that would be the largest is the sum. And then you would go to J1 plus J2 minus 1. And then you would keep going. And then the smallest one would be the absolute value of the difference.
Oh, so that wasn't 2j plus 1, was it? That was j1 plus j2, right?
Yeah, wait, I'm not sure what your question is.
It wasn't, I made a mistake. So it wasn't 2j plus 1, it was j1 plus j2, correct?
J1, this is adding angular momenta J1 and J2, which means it's a little confusing because when you're adding angular momenta, you're taking the tensor product of the Hilbert spaces. So I write a little circle time sign, but we say we're adding those two angular momenta.
Okay.
Okay? And then this is the result of adding them, is you get this direct sum.
So it's we just keep subtracting 1 from the sum until it gets to J1 minus J2.
That is correct, yes.
Hmm.
Right.
Okay.
So each thing in the sum is 1 less than the previous one until you get down to this one, and then you know you're done.
Okay. Thank you so much, Professor. Thank you.
Sure, no problem.
Have a great day. Bye.
All right, have a good day.
Bye.